This video is on theorems about continuity in metric spaces. Here we're going to relate continuity both to sequences and convergent sequences, as well as to open and closed sets in metric spaces. So first, let's just recall the definition of continuity for a metric space. So if xd and yd prime are metric spaces, and f is a function mapping x to y, then f is continuous at the point A in x if for every epsilon greater than 0, there is a delta greater than 0, such that the distance between x and A being less than delta in x implies that the distance d prime between f of x and f of A is less than epsilon in y. So that's our definition of continuity. So here's our first theorem. If we let f mapping, again the metric space xd to the metric space yd prime, and let A be an element of x, then f is continuous at A if and only if for every sequence x sub n in x that converges to A, the sequence f sub xn converges to f of A. So let's do our proof. Let's start in the forward direction. And for this, we're going to just do a direct proof. So let's suppose that f is continuous. Suppose f is continuous at A. And let's also suppose that we have some sequence x sub n that converges to A. Now we want to show that f of x sub n converges to f of A. In other words, what we want to show is that for any epsilon greater than 0, there is some n in the natural numbers such that when n is greater than n, the distance in y between f of xn and f of A is less than epsilon. So maybe I'll do implies here, such that n greater than n implies that the distance in y between f of xn and f of A is less than epsilon. That's the definition of f of xn converging to f of A. So far, we have our A in x, we have our f of A in y. We know that there is some sequence of points x sub n that converges to A. We want to show that f of x sub n converges to f of A. We also know by the definition of continuity that for any epsilon greater than 0, there is a delta greater than 0, such that the distance between A and x being less than delta implies that the distance between f of A and f of x is less than epsilon. So let's use that. So let's let epsilon be some arbitrary value greater than 0 by the definition of continuity. There exists some delta greater than 0 such that the distance between x and A being less than delta implies that the distance between f of x and f of A is less than epsilon. So how can we use that? Well, at some point, by the definition of convergence, these x sub n are going to be inside this ball of radius delta. So since the sequence x sub n converges to A, there is some n in the natural numbers such that n greater than n implies that the distance between x and A is less than delta. Oh, and this is. And so, well, if these x sub n are in this ball of radius delta, that implies that the f of x sub n are going to be in this ball of radius epsilon. So what we have is that n greater than n implies that the distance between x sub n and A is less than delta. Any x being in this ball of radius delta implies that f of xn is going to be in a ball of radius epsilon from f of a. So this implies that d prime of f of xn, comma, f of a is less than epsilon. And this is exactly what we want to show that f of xn converges to f of a. So therefore, f of xn converges to f of a. And we have proven the first direction of this theorem. Now to prove the converse, we're actually going to be doing the contrapositive of this. So what we want to show is that if for any sequence x sub n converging to a, f of x sub n converges to f of a, then the function f is continuous. So we're going to prove this using the contrapositive, and the contrapositive of the statement P implies Q is not Q implies not P. So in this case, what we want to show is that if f is not continuous, the negation of this statement, if for any blah, 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 the negation of for any is there exists. So I want to show if f is not continuous, there exists some sequence xn converging to a such that f of x sub n does not converge to f of a. So that's what we want to show. If we prove that, we will have proven the contrapositive, which means that we will have proven this statement. So let's suppose then that f is not continuous at a. Now what does that mean? That means that there exists some epsilon greater than 0 such that for any delta greater than 0, it can be the case that the distance between x and a is less than delta, but this does not imply that the distance in y between f of x and f of a is less than epsilon. So just unpacking this statement, that means there exists some x in x such that the distance between x and a is less than delta, but the distance d prime in y between f of x and f of a is greater than or equal to epsilon. So that's what that means for f to not be continuous. Okay, so what we want is we want to create a sequence x sub n that converges to a in x, where f of x sub n does not converge to f of a in y. This means this is for any delta greater than 0. So we could choose a sequence of deltas. Let's let delta be 1 over n for all n in the natural numbers. Then for this epsilon, for some epsilon greater than 0, it does not matter what our delta is. No matter what delta is, the distance between f of x and f of a will not be less than our epsilon. So for this epsilon, it's the case that there exists some xn such that the distance between a and xn is less than delta, but the distance between f of a and f of xn is greater than or equal to epsilon. This gives us such a sequence. This gives us a sequence x sub n converging to a, where f of x sub n does not converge to f of a. Our next theorem connects continuity in a metric space to open sets in a metric space. So it says that if we have a function mapping the metric space xd to the metric space yd prime, then the function f is continuous if and only if for each open set u of y, for any open set u in y, the set f inverse of u is open in x. Just a note, f inverse of u does not require the inverse of f being a function to be defined. So f inverse of u is a set, and it's the set of points x in x such that f of x is an element of u. So in other words, A is an element of f inverse of u if f of A is an element of u. Okay, so before we go on to prove this, I just want to mention that this is a really important theorem for us. In particular, in the next chapter, when we look at topological spaces, which are a more general version of metric spaces, we will be talking about situations where distance may or may not be defined. And so a topological space, instead of being defined by distance, is going to be defined by its open sets. So the definition of continuity is going to be exactly this for topological spaces, that a function is defined to be continuous if for each open set u of y, f inverse is open in x. So that's getting a little ahead of ourselves, but I just wanted to mention it to highlight this theorem. Okay, so let's get back to metric spaces. Let's now prove this theorem. So let's do our proof, and we'll start in the forward direction with a direct proof. So let's suppose that f is continuous, and we want to show that for each open set u of y, f inverse of u is open in x. So let's let u be an open set in y. And let's let A be an element of f inverse of u. In order to show that f inverse of u is open, we want to show that there exists some, let's say r greater than 0, such that the ball centered at A of radius r is completely contained inside of f inverse of u. That's the definition of an open set, or that's an equivalent definition to being an open set. So that's what we want to show. So we want to find such a ball. We don't have it yet, but we do know that u is open. So since u is open in y, that means there is some epsilon greater than 0 such that the ball centered at f of A of radius epsilon is completely contained inside of the set u. Okay, now let's use continuity. So since f is continuous, there exists some delta greater than 0 such that the distance between x and A being less than delta in x implies that the distance d prime between f of x and f of A in y is less than epsilon. So in other words, let's change colors. We've got some we've got some epsilon ball that's completely contained inside of u. That means there exists some delta such that the ball for any element x that's of distance less than delta from A, that element x will be of distance less than epsilon from f of A. So what do we have? So that means that distance between x and A less than delta implies that f of x will be of distance less than epsilon from f of A. In other words, f of x is in the ball centered at f of A of radius epsilon, and that we know is completely contained inside of u. So that tells us that f of x is in u. In other words, x is an element of f inverse of u. So what we have is that the distance between x and A being less than delta implies that x is an element of f inverse of u. That is, the ball centered at A of radius delta is completely contained inside of f inverse of u. So we have shown that f inverse of u is open. Therefore, f inverse of u is an open set. Let's now show the second half of this theorem, that if it's the case that for any open set u subset of y, f inverse of u is open in X. If that is always true, then f is continuous. So we're going to assume that this is true. We want to show that f is continuous. In other words, we want to show that for any epsilon greater than 0, there is a delta greater than 0, such that the distance between x and y being less than delta implies the distance in y between f of x and f of y is less than epsilon. So we want to show something in terms of epsilon delta definition of continuity. What we know is about open sets. So let's think about how we could translate that. We know that any ball of positive radius is an open set. So let's use that. Let's let A be an element of X, and we want to show that f is continuous at A. A is an arbitrary element of X, so if we show f is continuous at A, then f is continuous everywhere. So let A be an element of X, and let epsilon be greater than 0. So we have A over here, and f of A over there. We know that the ball centered at f of A of radius epsilon is an open set in Y. By our hypothesis, that means that its inverse, f inverse of the ball centered at f of A of radius epsilon is then open in X. So we've got this ball of radius epsilon, and this is ball centered at f of A of radius epsilon. The set, which is the inverse of that, f inverse of the ball centered at f of A of radius epsilon must be an open set. In fact, it's not a ball, it might be just some weird set. But because it is open, because it is open, that means there exists some delta greater than 0 such that the ball centered at A of radius delta is completely contained in this set, in f inverse of the ball centered at f of A of radius epsilon. How do we know? It's our definition. Well, it's one of the equivalent definitions of being an open set. We know that A is an element of this set because f of A is in here. So because f of A is in this set, that means that A must be an f inverse of that set. So we have that the distance between X and A being less than delta tells us that we are in this set, which means that X is an element of f inverse of the ball centered at f of A of radius epsilon. And that tells us then that f of X is in this set. That's the definition of, or in this set. That tells us that f of X is an element of the ball centered at f of A of radius epsilon. If X is in the inverse of the set, then f of X is in that set. And that tells us then that the distance in Y between f of X and f of A is less than epsilon. And so we've got our definition of continuity, that the distance between X and A being less than delta implies that the distance between f of X and f of A is less than epsilon. The last theorem in this section relates continuity to closed sets. So it says that if f is a function mapping a metric space xd to a metric space yd prime, then f is continuous if and only if, for each closed set of C, f inverse of C is closed in X. So before we get to the proof of this theorem, let's just prove something intermediary. Let's prove this claim that if f maps x to y and b is a subset of y, then x minus f inverse of y minus b is the same thing as f inverse of b. In other words, this is f inverse of y minus b complement, and we want to show that that's just f inverse of b. So we've got our function over here, and here is the set y minus b as a subset of y. Then when we look at f inverse of y minus b. That's some set that maps over to the blue region over here. Maybe it's connected, maybe not, whatever. So we've got that set. Now let's suppose that we've got some other element, x, which is not in there. So x is an element of x minus f inverse of y minus b. X is outside of that set. If and only if, well, where could x go? So x can't go out here because we've said that x is not an element of y minus b, so no. So that means that the only other place for it to go, if it's not going in b complement, then it must go in b. So f of x must be an element of b. So if and only if f of x is an element of b, and that's true if and only if x is an element of f inverse of b. So that was just a quick thing to note, because the proof of this theorem is going to use this duality between open and closed sets. Recall the initial definition of a set being closed is that a set is closed if its complement is open. So basically we can use the previous theorem plus the definition of a closed set to prove this new theorem. Okay, so we now want to prove that f is continuous if and only if for each closed set C in Y, f inverse of C is closed in X. So let's draw our picture that we've been drawing. We've got f mapping xd, the metric space, to yd prime, the metric space. And we've got some closed set C in Y. We want to show now that f inverse of C is closed in X. So since f is continuous, and, well, C is closed, so C complement equals y minus C is open. That tells us that f inverse of y minus C is open by our previous theorem. Our previous theorem said that if u is open in y, then f inverse of u is open in x, and this is just our u. Okay, so this is open in x, and therefore, by definition of a closed set, x minus f inverse of y minus C is closed in x. But as we saw above, x minus f inverse of y minus C is just equal to f inverse of C, as we saw above. So this is closed. And so we've done the first half of this theorem. So we've done this proof. And the other half of the theorem is going to be a homework problem. So you can use that little note above about the equality of these sets, use the previous theorem, and also use the fact that the definition of a closed set is that its complement is open.